So you know very well that for this question the correct option is here they have asked they have given a relation here. We need to find out the correct option. Okay, I have told you all Maxwell relations, whatever Maxwell relation you take, the relations involves pressure, volume, temperature and entropy. Okay, all the relations involve pressure, volume, temperature and entropy, right? And here what is given? Dou S by dou V at constant pressure is given. Okay, I have given you a trick to identify this. What is the trick? Now in this given derivative, entropy is there, volume is there and pressure is there. Entropy, volume, pressure, all the three terms are available. Which one is left with?
Temperature.
Temperature. Okay, yeah. So write temperature in the numerator. Bring the pressure inside and volume outside. Dou P at constant volume. Okay, and I have told you it is very important. Within the bracket, if we have temperature and volume, okay, right? If you have temperature and volume inside the bracket, above temperature, below volume, or above volume, below temperature, whatever it is, then you must put negative sign. But in this case, we have temperature and pressure inside the bracket, so the quantity is positive only. So the correct option is, according to Maxwell relation, this is equal to dou T by dou P at constant volume, which is option B. Okay, take note. Listen, for a closed system containing a pure gas, dou H by dou S at constant pressure equal to, okay, see, enthalpy is there and entropy is available, enthalpy and entropy. So equation which connect enthalpy and entropy, dH is equal to, it's a standard equation, dH equal to TdS plus VdP. We know this. We know this equation, standard equation. Now what I am going to do, listen, we should keep pressure constant. Okay, pressure constant. Constant pressure means dP is 0, correct? At constant pressure, dP equal to 0. So put dP equal to 0. If dP is 0, this entire term becomes 0. So you will get dH is equal to TdS. Bring the ds to the left hand side. T into ds is there. Bring the ds to the left hand side. So dou H by dou S at constant pressure equal to T. Dou H by dou S at constant pressure equal to T. Okay. The correct option for this question is option A. Take note. For this question, okay, Kirchhoff's equation is a very famous equation. For this question, the correct option is option C. Directly we can answer delta H2 equal to delta H1 plus delta of Cp into T2 minus T1. This equation is called Kirchhoff's equation. Okay. Now, what is the meaning for this? Suppose some chemical reaction is given, reactant gives product, some chemical reaction. Okay. Now, what to do? You carry out this reaction at some temperature T1 and find out the enthalpy change. Okay. You carry out some chemical reaction at temperature T1, at constant temperature T1 and find out delta H. Okay. That delta H is actually called delta H1. You know very well, and here pressure should be constant. In this reaction, we keep pressure constant. At constant pressure and at temperature T1, we carried out the reaction and we got the enthalpy changes delta H1. You know very well, at constant pressure, enthalpy change delta H is equal to, okay, integral T1 to T2 at constant pressure, T1 to T2, right? N CPM or simply Cp, Cp into dt. Okay, this equation you know. Listen, I'll keep this one as such. Okay, I'll keep this one as such. We'll connect how this equation, how this equation changes into the Kirchhoff's equation, right? How to get that, we'll discuss. Now, you carry out the same reaction at the same pressure but at a different temperature T2. You carry out the same reaction at the same pressure and at different temperature T2 and find out the enthalpy change here, delta H2. Okay, so if you change the temperature of the reaction, enthalpy also changes. Okay, now to find the change in enthalpy, what to do? Right? Listen, this is the finite integral, finite enthalpy. Right? For infinitesimal change, we'll write like this: dH is equal to, okay, Cp into dt for infinitesimal change. Right? Then to find the complete change, what to do? Okay, we differentiate this d of change in enthalpy, d of delta H equal to differential of Cp into dt. Now we have to integrate. Okay, so you'll get enthalpy change at temperature T2. Okay, I'm just integrating from initial temperature T1 to a final temperature T2. Okay, minus enthalpy change in the initial state, that is delta H1, equal to dCp. You can also write this delta Cp. Delta Cp. Suppose assume that delta Cp is constant. Okay, it is independent of temperature, suppose. Then you can take this delta Cp out. So delta Cp into integral dt is T, upper limit T2, lower limit is T1, so T2 minus T1. Okay, or you can also write it as delta H2 equal to delta H1 plus delta Cp into, T2 minus T1. This equation is what we call as Kirchhoff's equation. Listen, it's very simple. The point here is, if you change the temperature of a reaction, the enthalpy change, delta H, also changes. Okay, so if enthalpy change at temperature T1 is delta H1 and enthalpy change at temperature T2 is delta H2, and if delta Cp, okay, delta Cp of the reaction, if it is independent of temperature, then you will get an expression like this. This is called Kirchhoff's equation. Okay, take note. This is question number 4. Which among the following is a partial molar property? Yes. Yeah, I have told you for partial molar property, what are the quantities we should keep constant? Temperature, pressure, number of moles of all the components except the ith component. Okay, yes. Okay, and inside the bracket you may have any term here, but in this case the only option which has temperature, pressure and number of moles of all the component constant except I, okay, is option D only. Therefore, the correct option for this question is option D. Okay, for any partial molar property, we should keep temperature, pressure, number of moles of all the component except the ith component. We should keep all these things as constant. Okay, then that quantity is called as a partial molar property. Okay, take note. This question we have already discussed anyway. Which among the following is correct for a real gas? Listen, option A, it is given that fugacity equal to pressure. You know very well, for ideal gas, yes, fugacity and pressure are equal. They are one and the same for ideal gas. Okay, then fugacity coefficient, gamma. Fugacity coefficient is nothing but fugacity of the gas divided by pressure. This ratio is called fugacity coefficient. Okay, and it is given that fugacity coefficient is a constant. Listen, for ideal gas, okay, fugacity coefficient equal to 1. It is a constant, yes. For ideal gas, it is a constant. Whereas for a real gas, for real gas, I have told you, for real gas, okay, F is not proportional to pressure. F and P are not proportional. They are not proportional to each other. Therefore, fugacity coefficient is not a constant. Okay, for different pressure values, okay, you will get different fugacity, and the fugacity by pressure, that ratio is not a constant. So gamma is not a constant. Keep this in mind. Very important, because fugacity and pressure are not proportional. Yes, the correct option is C. See the option C? Fugacity is not proportional to pressure. Yes, correct. It is not proportional. Okay. Then in option D, see, for all real gases, F is less than P is given. Listen, for most of the real gases, F less than P is correct. But there are gases for which fugacity value may be greater than pressure. Example, helium, hydrogen gas. I have given few examples, right? So just go through this question carefully. A graph is given where alpha is plotted against pressure, and they got some graph is given here, and they have found out the area up to 100 atmosphere pressure. Okay, and the area is given, it is equal to 0.2 RT. The question is the fugacity of the real gas. So this plot corresponds to some real gas. The fugacity of the real gas at 100 atmosphere pressure. Okay, so what is the fugacity at 100 atmosphere pressure as per the above plot? 4 options are given here. Listen, alpha is given, so you must know what is the relation between fugacity and alpha. Listen, ln fugacity by pressure. This is applicable for pure gas. You know very well. Okay, if you have a pure gas in a container, you can use this formula. Ln fugacity by pressure is equal to minus 1 by RT integral 0 to P into alpha into dP. Okay, this equation you know very well. We derived it. Now what to do? Keep this minus 1 by RT as such. Okay, up to 100 atmosphere, 0 to 100 atmosphere pressure they are asking. Okay, 100 atmosphere, alpha into dP. Okay, this area is actually available here. Up to 100 atmosphere, the area is given. So that area corresponds to this integral. The value of the integral is equal to the area. Area is given now, so you can directly write minus 1 by RT into the area is 0.2 RT. So this RT cancel, you will get minus 0.2. This is the value of ln F by P. So what is F by P? Therefore, F by P, if you remove log, you must put e power minus 0.2. Yes, this quantity will go to the power of e power minus 0.2. E power minus 0.2 value is given here. Okay, 0.818. So F by P equal to this. Then what is F? Let me write here. Therefore, F is equal to, yes, 0.818 into P. Okay, we need to find out the fugacity at 100 atmosphere. So into 100, if I multiply, I'll get 81.8 atmospheres. Yes, this is the fugacity of the gas at 100 atmosphere pressure. Okay, take note. Therefore, the correct option for this question is option B. Right? Take note. Listen, just go through the question carefully. It is given that delta H for an isobaric heating of a gas. Isobaric means constant pressure, and we are heating the gas. So heating means temperature increases. So what is the delta H for that? Listen, you know very well. Change in enthalpy dH is equal to this formula, you know. Okay, dou H by dou T at constant pressure into dt plus dou H by dou P at constant temperature into dP. This you know very well. It's a standard equation for enthalpy. Now, at constant pressure, if you keep pressure constant, then dP becomes equal to 0. So if you put dp 0, then this entire term becomes 0. Therefore, we get dH is equal to dou H by dou T at constant pressure into dt. This quantity is nothing but Cp. Okay, so dH is equal to Cp into dt. What is Cp? You know very well, N into Cpm. Cp means heat capacity for N mole of gas. Cpm means heat capacity for 1 mole of gas into N will give you N mole. So in the place of Cp, I can write dH is equal to N into Cpm into dt. Okay, this is dH. Now we should find out delta H. Okay, so delta H means you need to integrate this. So integral, and we are heating it, so temperature increases from T1 to T2. N into Cpm into dt. Right? So this is the correct equation. So the correct option for this question is option A. Right? In option B, you observe this carefully. R plus Cvm equal to Cpm. Yes, correct. R plus Cvm. Okay, Cvm, you know your Cpm minus Cvm equal to R. Listen, Cpm minus Cvm equal to R. Then what is Cpm?
R plus Cvm.
R plus Cvm, right? R plus Cvm. Yes, instead of Cpm, we have R plus Cvm. You may think that this also correct. This option also correct? See, here Cpm is there. Instead of Cpm, it is given that R plus Cvm. Yes, but this is applicable only for ideal gas. If you use this formula, that is applicable for ideal gas. But here, they did not mention whether the gas is ideal or not. Okay, so you have to use the general equation, right? Not this one. This is applicable only for ideal gas. Right? Therefore, this option is not correct here. Okay, take note. So the only option which is correct is option A. Right? Take note. Right. First go through the question. For a reversible isochoric, reversible is given. Isochoric means volume constant.
Yes.
Heating is given. Heating means temperature increases. And it is given that ideal gas. You know very well, for ideal gas, for ideal gas, to find entropy change of the system, this is actually system entropy. Entropy change of the system, there are two formulas available. Number one, N into Cvm integral, N into Cvm into dt by T. Okay, plus integral nr into dv by v. This is v1 to v2, volume increases, okay, and temperature T1 to T2. This is equation number 1. We have another equation actually, we'll write in the next page, but before that, I'll give answer for this question first. This equation is applicable for reversible process. I am using equal to symbol here, so it is applicable for reversible process. Right? Isochoric means volume is constant. So at constant volume, dV becomes 0. Therefore, the second integral becomes 0. So we get delta S system is equal to integral T1 to T2 N into Cvm into dt by T. Yes, the correct option for this question is option A. Take note. We have one more equation to find the entropy change of system for ideal gas. The second equation, see, this equation is applicable only for ideal gas. Second equation is delta S system equal to integral T1 to T2 N into Cpm into dt by T plus integral P1 to P2 in terms of pressure nr ln dP by P. nr ln dP by P. Okay, and actually this should be minus sign, minus. Right? Take down this. This is the formula. This second formula available to calculate entropy change of system for ideal gas. But if you want to use this formula, you should mention about pressure. If pressure is constant, suppose if it is isobaric process, isobaric means this term becomes 0, you will get this answer. But it is mentioned clearly that the iso is a isochoric heating. Since it is isochoric heating, volume should be constant. Therefore, the correct option is this. Okay, this one. So the correct option for this question is option A. Take down. Okay, for an it is given clearly ideal gas, and they are asking dou H by dou P at constant temperature. You know very well, for ideal gas, okay, internal energy is a function of temperature only, I have told you. Similarly, enthalpy also a function of temperature only for ideal gas. If we keep temperature constant, see here, temperature is constant. If we keep temperature constant, then there is no change in internal energy, there is no change in enthalpy. So, keeping temperature constant, if we change the pressure, will enthalpy change? No. So, the correct option is B. Right? You can answer this question directly like this. Okay, take down. Yes, just go through this question. 5 moles of an ideal gas undergoes a reversible, see, ideal gas is given, reversible process. It is a reversible process. What is actually happening here? The gas moves from initial state 2 atmosphere 5 liter to a final state 1 atmosphere 20 liters. The question asks is delta G minus delta A for the processes. Yes, you know very well. G is equal to, okay, G is equal to H minus Ts. G is equal to, H is nothing but U plus PV minus Ts. And we also know that A is equal to U minus Ts. So, here we have U, here we have Ts. So, U minus Ts is A. Therefore, I can write this as G is equal to A plus PV. Okay. Therefore, change in free energy delta G equal to delta A plus delta of PV. Okay, change. So, to find change, use this formula. Bring delta A to the left hand side. Delta G minus delta A. This is what, delta G minus delta A. This is what we need to find out. Is equal to delta of PV. What is delta of PV? P2V2 minus P1V1. Final pressure volume minus initial pressure into volume. Okay. What is the final pressure and final volume? Final pressure is 1 atmosphere. Final volume is 20 liters. If I multiply these two, I will get 20. 1 into 20. Minus initial pressure, initial volume. Initial pressure is 2 atmospheres and initial volume is 5 liters. Okay. So, what we get is 20 minus 10, which is nothing but 10. The unit is, we are multiplying these two, so the unit is liter atmosphere. And I have told you already, 1 liter atmosphere equal to 101.3 joules. Okay, so if you multiply this by 101.3, 10 into 101.3, I will get the answer in joule, which is equal to 1013 joules. Take down. It's a very simple question. So the correct option for this question is option C. Take down.